I am Sheikh Rashidur Rahman, Assistant Professor, Department of Electrical and Electronic Engineering, University of Asia Pacific. So today I am going to deliver my second lecture about per unit calculation. So per unit calculation is a very interesting topic in power system analysis. And already in my last lecture, I have discussed the equation which we need to study to solve the per unit calculation of any power system actually. So before start our new session, I want to recall something of my previous lecture. At first, what is the online or single line diagram? At first, I have to describe again the conception of online or single line diagram. So in a power system, we know that the power system is a three-phase power system. So there are three lines actually. It represents the three-phase power system. This is a transformer. Definitely, this is a three-phase transformer like this. So this is three-phase transformer actually, and this is generator. Definitely, this is a three-phase generator, and so go on. But this is a three-phase balance system. So the power flowing through every phase is equal. We know the equation of three-phase power system. If we add the power of phase A plus phase B with phase C, we will get the total power delivered through the sending end to the receiving end by this three-phase power system. So this is a balance system. Now for this balance system, instead of presenting this three-phase line, we can present this system by a single line actually. And this is called single line diagram or online diagram. So this is also a three-phase transformer, and this is also a synchronous generator or three-phase generator, and this is a three-phase transmission line. But regarding this is a balance system, we can replace this system by this single line system. So we replacing the three-phase system by the single phase or single line system. That's why it is called single line or one line diagram. So it is called single line or one line. So it is called single line or one line diagram. It is called single line or one line diagram. So this diagram is called single line or one line diagram. So this diagram means this is not a single phase system actually. This is a three-phase system. But instead of drawing this three line, we can represent this by a single line because this is a balance system. So if we calculate the power of the single line, we can multiply it by 3 and we will get the power of three-phase line. So this is called one line or single line diagram, or this is the conception of one line or single line diagram. Now, the second thing I want to recall, that is the equations of per unit calculation. So there are mainly three equations in per unit calculation. So at first, this is the basic equation or basic definition of per unit calculation. That is, if we want to calculate the per unit value of a quantity, then we have to divide the value of the real unit of the quantity by the base value or reference value in the same unit of the quantity. It means that if we want to calculate the per unit value of impedance, then we have to divide the real value of impedance with the base value or reference value of the impedance. So this is the basic definition or the basic equation of per unit calculation. This is equation number 1. The equation number 2 is, if there are actually two different values of power actually. If we simplify this, that one per unit value is given in our question for a particular device, like we have given a per unit impedance value of transformer that is 10%. In the base of 50 MVA power rating and 20 kilovolt voltage rating. So we have a value of per unit reactance or impedance of a transformer that is 10%, or the value is 0.1 per unit, with the base or reference of 50 MVA power rating and 20 kilovolt voltage rating. Now, if we want to calculate the per unit value of this transformer once again with the new reference value of power and the new reference value of voltage, or a new reference value of power with the old reference value of voltage, or with the new reference value of voltage with the old reference value of power, then we should have used this equation. That is, the new per unit value of the device is equal to the old or given per unit value of the device into the power rating of the device, which is new. It means that in which rating we have to calculate the value, divided by the power rating of old. It means that in which rating the impedance per unit value is given in the question, into the old rating of voltage base square. This means that the value in which the impedance value is given in the per unit question, and divided by the voltage base square new value. It means that in which voltage we have to calculate the new per unit of the device. So this equation we will use if we have two new value of power and voltage and two new base value of two old base value or given base value of power and voltage with a given value of per unit impedance of the device. Then we will use this equation. And the third equation is only applicable for transformer. That is, we know transformer is a device which transmit power from primary to secondary, but it will change the voltage level from primary to secondary if the transformer ratio is not 1:1. So if the transformer ratio is not 1:1, then the base voltage of the primary side will not the same as the base voltage of secondary side. So we have to calculate the base voltage of transformer secondary portion from primary portion by using the equation V1 by V2 is equal to E1 by E2. So this is the equation. So these are the topic at first I just recall from my previous lecture. Now one thing I didn't say about it. Actually, I didn't say it about anything. That is the advantage of per unit calculation. Actually, why we calculate the value in per unit of a particular device, and finally, why again we just shifted this per unit value to a real unit value. So, what is the reason from shifting the real unit value to per unit value? What is the reason actually? There are several advantages regarding this per unit calculation. At first, it is a little bit complex to handle different types of quantity with different unit in a mathematical problem. It is kind of bothering situation actually. To rid of this situation, we can convert the unit with all quantity to a same unit, that is per unit, so that we don't need to think about anything regarding the unit whenever we calculate something. So this is one of the advantages, that we can handle different quantity in our mathematical problem with the same unit. So we don't think, but we don't need to think about the unit. So this is the first advantage. Our second advantage is, in a power system actually, this is an interconnected power system. Here generation is connected to transmission, then transmission is connected to distribution, and there are several devices connected through this process, like protecting device, fuse, relay, circuit breaker, or the step up, step down transformer, or the current transformer, potential transformer, synchronous generator. So there are several devices connected throughout this process, and every devices has their own reactance or has their own impedance in their own rating or based on their own rating. It means that whenever you purchase a synchronous generator for your use, this generator has a particular reactance like zero point 0.1 ohm, sorry, zero point 0.1 per unit. And this reactance is based on their own rating. That is, their rating is 50 MVA, their voltage rating is 20 kV. So let's have a guess that a synchronous generator is reactance is like 5 ohm, the machine reactance 5 ohm, based on their impedance, based on their power rating and their voltage rating. But whenever you connect this device with a transformer, it means that with other device, then this transformer has a particular reactance with his rating, based on his rating. Like the transformer has a reactance of like 5% or 10% with his power rating 20 MVA, voltage rating 10 kilovolt. So the reactance of generator and the reactance of transformer are different with their different rating, based on their different rating, but they are connected together because the transformer is connected to the synchronous generator. So whenever we want to calculate the voltage, current, or the power for this type of transmission line, actually, these devices are connected together. So we have to consider the reactance of these two devices. But these reactance are different based on their machine rating, because their machine rating are different. So to solve the problem, at first, we have to convert this reactance with a same rating, with a flat reference rating. So if we assume that our generator and our transformer are same power rating and they are the same voltage rating, but their reactance should be different from their rating value, because now we have converted this reactance based on a new reference value, and this is necessary because now the transformer and generator are connected together. So that's why we just convert these devices with a same reference or base power and base voltage rating. And for doing this, we have to convert the reactance value with the change of the rating value or new rating value. So this is the advantage of per unit calculation. That is, we convert this value with a reference value, and after calculating the per unit value with the new reference value, we can easily solve this kind of mathematical problem, or we can easily calculate our current voltage or power in our interconnected system. So this is one of the advantages to convert it, the reactance value with the per unit value based on their rating or based on our new reference value. And the third and the most important thing is, in a power transmission line, there should be a transformer connected, and there are several transformers actually connected regarding a step up, step down, one-to-one transformer, auto transformer, distribution and transformer. There are several transformers connected, and we know that the primary side resistance value of the transformer and secondary side resistance value of the transformer are not same. So if I want to convert the resistance value from primary to secondary or secondary to primary, we have to use this kind of equation to convert our resistance actually from primary to secondary or secondary to primary whenever we draw an equivalent circuit of transformer. But whenever we represent the reactance or impedance value of a transformer by the per unit value, then this per unit impedance or reactance of the transformer is same regarding we refer it primary or secondary. So this is a huge advantage. That is, we don't need to think about the per unit reactance value of the transformer, either it is in primary portion or it is in the secondary portion. We just replace the transformer by a single reactance or impedance regarding, don't think about the primary or secondary. We just replace the device by a single per unit reactance or impedance. So the per unit reactance or impedance of a transformer is same in the primary and the secondary side. So this is a huge advantage whenever we calculate the power system, the voltage, current, or power transmission efficiency, anything, because this is a huge concern regarding the transformer. But whenever we represent the reactance or impedance in per unit of a transformer, then we don't think about the primary or secondary side. The impedance or reactance of per unit of the transformer is same at the primary side and the secondary side. So this is a huge advantage. And not least, but the number 4 is, in the manufacturer, who are just manufacture different device, electrical device like transformer, generator, or synchro or motor. They all are write the reactance or impedance in their nameplate in per unit form. So whenever you will buy a 3-phase induction motor, you will get that the reactance value of this induction motor is 0.5 per unit based on their own rating. So the manufacturer are use per unit value to indicate the reactance or impedance of the particular device regarding their own rating, power and voltage rating. So that's are the importance to calculate the reactance or impedance in per unit formation or in per unit form. So I think now you should understand the importance of per unit calculation in power system. So that's the reason in my previous lecture I have said that we need to understand this per unit calculation in very clearly, so that in our future topic we can use this per unit calculation conception to into the other mathematical uh, problems to solve those problems actually. So this is so much important topic, and you have to understand this topic very clearly, and that's the reason I will try to discuss this topic actually elaborately, so that you can easily understand the conception and the calculation procedure of per unit. Now, in my today's lecture, I want to actually solve this mathematical problem, and this is a per unit mathematical problem. So this is actually a online diagram or a single line diagram. So this is a online or single line diagram. So this diagram represent that this is a synchronous generator connected in bus 1. This is bus 1. So what is the bus actually? Bus is nothing but a node. And what is node? Node is a point where different devices are connected together. So this is we called node. So bus is basically a node where different device or more than one device are connected together. In power system, instead of saying node, we say it bus. So this is the bus number 1, and in bus 1 a synchronous generator is connected. So this is the generating unit, and this is the parallel line, that is two transmission line are connected together. So this is a double circuit transmission line. This line, this is the line 1, this is a three-phase transmission line, and this is line 2, this is also a three-phase transmission line. These two are the three-phase transmission line, but they are two separate three-phase transmission line. It means that this is a double circuit parallel transmission line, and these two parallel transmission line are supplied by this generator. It means that this generator supply the power of both these two transmission line. Now, this is transformer 1 connected with bus 1. So this is basically a step up transformer. We know from the generation unit, we need to step up the generation voltage. If the generation voltage is 33 kV, at least we need to step up this voltage at 132 kV to transmit the power from sending end to receiving end, or more than 132 kV. That is a second step, we can convert it 230 kV or more than 230 kV to transmit the power from sending end to receiving end. So this is a step up transformer. Basically it step up the voltage. After getting the high voltage, the secondary portion of the transformer is connected to the other transformer, that is called transformer 2, and this connection is transmission line actually. So this is the transmission line, and this should be a high voltage transmission line, because if the generation is 33 kV and this transformer is step up the voltage from 33 to 132 kV. So this line is the high voltage transmission line, because now the 132 kV is transmitted through this line. This high voltage transmission line connects through that, say, transformer 2, and this transformer is the step down transformer, because this is the distribution side whenever we need to step down the voltage. And this step down transformer connected to the load. This is a load and a motor. So motor is also a load, but this load is defined as a motor, but this load is not defined as a motor. So it may be, or it can be a motor, or it can be a anything like any other inductive load or any other types of load. And this is the second parallel circuit. Here there is also a step up transformer, and this is a high voltage transmission line, and this is a step down transformer, and this is connected through the bus 4. So this is bus 4, and this connection is the with the motor and the load. So here there are 6 buses or 6 connection point actually defined as a bus. This is bus 1, bus 2, bus 3, bus 4, bus 5, and bus 6. So we can say in bus 1 connection, the generation side is connected through bus 1. The connection between bus 2 to bus 3, this is a high voltage transmission line 1. The connection between bus 5 to bus 6, this is a high voltage transmission line 2. And the connection in bus 4, this is the distribution side connection, where the load are connected through the lower voltage portion of the double circuit parallel transmission line. So now, at first, to solve the question, we need to understand the question actually, that is what are really saying about the question, or what the question does mean actually. So this diagram is called the one-line diagram, because all other devices are 3-phase devices, but instead of this 3 transmission line or 3-phase line, we replace is by a single line. So this is a one-line or single line diagram of a particular power system. This particular power system, there are 2 double circuit parallel transmission line, there are 4 transformers, there are 1 single synchronous generator, and 2 load. So this is the particular online or single line diagram of a power system. Now the question is, select common base of 100 MVA and 22 kV on the generator side. It means that the question said that in generation side, we have to select a common power base of 100 MVA and voltage base of 22 kV. Draw an impedance diagram with all impedances, including the load impedance marked in per unit. So we have to draw a reactance or impedance diagram of this power system, and we have to mark the all devices reactance, including the transmission line, in per unit value, with the based on these new reference power and voltage value. So we need to draw a reactance diagram. So at first, actually, we need to determine the per unit reactance value of these all devices, including the transmission line of this particular power system. In this question, the per unit reactance value of all devices are given here. That is a generator, transformer 1 to 4, and the motor. Their power rating, their voltage rating, and their reactance are given there. And this reactance is percentage. It means that all these values are per unit based on this particular rating. And the 3-phase load connected in the bus 4, the rating of power is 57 MVA, the power factor is 0.6 lagging, that is the inductive load, and the voltage is 10.45 kV of this particular load. Transmission line 1 and 2 have reactance of 48.4 and 65.43 ohm respectively. So the transmission line reactances are also given here. Now we need to calculate the per unit value of all of these devices, including the load and transmission line, with the new reference value. One thing you have to understand, that is, the generator reactance is 18%, that is the 0.18 per unit is given in the question, with the base of 90 MVA power and 22 kV of voltage. But in our question, we have to calculate the generator reactance, that is the per unit reactance, once again with the new power base of 100 MVA and with the new voltage rate base of 22 kV. So the two new power and voltage base are given in our question, and for every devices, old voltage and old power base are given in the question, and regarding this old power and old base voltage, old reactance value of per unit is given in the question. So whenever we have to solve this particular type of mathematical problem, we need to apply the equation number 2 to calculate the per unit reactance, because in this equation number of 2, actually, which is marked in my slide in 10, that is, if we want to calculate the new per unit reactance of a device, then this is the equation. Actually, this is the equation. So we have to apply this equation, because here for every devices, the old voltage rating and power rating are given with the old reactance value. We have to calculate the new reactance value with the new power and new voltage rating. So in this question, actually, whenever we want to solve this mathematical problem, we know that the base voltage of the transformer primary side to single side may be changed if the transformer ratio is not 1:1. So we have to calculate the base voltage of every point of connecting device or all connected device to solve the mathematical problem. So at first, now to solve the problem, at first we calculate the base voltage. The base voltage VB1 on the low voltage side of transformer is 22 kV. This is given in the question rating. This is given in the rating actually. That is for transformer 1. That is for transformer 1. The base voltage is 22 by 220 kV. This 22 by 220, it doesn't mean we have to divide this 22 by 220. It means that one rating is given for the primary portion and other rating is given for the secondary portion. So these 22 and 220 kV, here 22 is the low voltage portion, should be connected with the low voltage side of the transformer, and 220 kV should be connected with the high voltage side of the transformer. And this rating is given for T1. So here this is the T1 transformer. So 22 is the low voltage portion, and transformer low voltage portion should be connected with the generating unit or with the load unit. So this 22 kV is placed in here, in point here. This is the primary portion, because this 22 is connected with the low voltage portion and this is connected with the terminal of generator. And the 220 kV, the high voltage rating, this should be connected with the high voltage transmission line. That is 220 rating is the secondary portion of the transformer T1. Now, for transformer T2 actually, this 220 is the high voltage rating and that should be connected with the high voltage transmission line. That is here, high voltage transmission line. So 220 is the rating of the transformer high tension side, and 11 kV, that should be the rating of transformer low tension side. That is here. that is connected with the load. Similarly for transformer T3 and T4. So একটা কথা এখানে পরিষ্কারভাবে তোমাদেরকে বলে দিই, কয়েকটা বিষয় কোশ্চেন থেকে তোমাদেরকে খুব ক্লিয়ারলি জানা দরকার। সেটা হচ্ছে কোশ্চেনে ট্রান্সফরমারের ভোল্টেজ রেটিংটা 220/2020 থাকতে পারে, আগে 220 থাকতে পারে, পরে 2020 থাকতে পারে। তোমাকে ট্রান্সফরমারের রেটিংটা ধরতে হবে ট্রান্সফরমারের যে পোর্শনটা জেনারেটরের সাথে কানেক্টেড থাকবে সেই পোর্শনটা অলওয়েজ লো ভোল্টেজ পোর্শন। সো যদি তোমার সামনে 220 থাকে, তারপরেও পরে যদি 22 থাকে, এই 22টাই বসবে হচ্ছে প্রাইমারি সাইড, দ্যাট ইজ যে পোর্শনটা কানেক্টেড জেনারেটরের সাথে, সেই পোর্শনের রেটিং হিসাবে। এবং ট্রান্সফরমারের হাই ভোল্টেজটা অবশ্যই সবসময় ট্রান্সমিশন লাইনের রেটিং। সো এই 220 এটা হচ্ছে ট্রান্সমিশন লাইনের হাই ভোল্টেজ পোর্শনে বসবে ট্রান্সফরমারের। সিমিলারলি আমি যদি T2 এর কথা বলি, তাহলে 11 কেভি এটা হচ্ছে লো ভোল্টেজ সাইডের রেটিং। সো 11 কেভিটা বসবে যে পোর্শনটা ট্রান্সফরমারের লোডের সাথে কানেক্টেড সেই পোর্শনের রেটিং হিসাবে। আর 220 হাই ভোল্টেজ পোর্শনের রেটিং এটা বসবে ট্রান্সফরমারের হাই ভোল্টেজ ট্রান্সমিশন লাইনের সাথে। তো কোশ্চেনে তোমাকে 220/22 থাকতে পারে, তো তোমাকে কোনটা কোন পোর্শনে বসবে সেটা তোমাকে এভাবে আইডেন্টিফাই করে নিতে হবে। তাহলে ট্রান্সফরমারের হাই ভোল্টেজ পোর্শনটা অলওয়েজ ট্রান্সমিশন লাইনের সাথে কানেক্টেড থাকবে, ট্রান্সফরমারের লো ভোল্টেজ পোর্শনটা অলওয়েজ হয় জেনারেটরের সাথে, না হয় লোডের সাথে কানেক্টেড থাকবে। আরেকটা কথা হচ্ছে যে এই ধরনের ম্যাথ সলভ করার সময় আমরা যে বেস ভ্যালুটা কোশ্চেনে দেওয়া থাকবে, এই বেস ভ্যালুটা আমাদের টোটাল পাওয়ার সিস্টেমের অনলাইন ডায়াগ্রামে যে ডিভাইসের সাথে ম্যাচ করবে সেই ডিভাইস থেকে ক্যালকুলেশনটা শুরু করতে করতে আসতে হবে। যেমন এখানে 22 কেভি আমাদের বেস ভোল্টেজ কোশ্চেনে দেওয়া আছে, নতুন বেস, যেটার উপরে ভিত্তি করে তোমাকে ম্যাথটা সলভ করতে হবে। এই বেস ভোল্টেজটা আমার এই পাওয়ার সিস্টেমের মধ্যে দেখো জেনারেটরের সাথে ম্যাচ করতেছে। সো আমাকে জেনারেটর থেকে পার ইউনিট ক্যালকুলেশনটা শুরু করে এই পর্যন্ত আসতে হবে। তোমরা বলতে পারো যে এটা ট্রান্সফরমার 1 এর লো ভোল্টেজ পোর্শন অথবা ট্রান্সফরমার T3 লো ভোল্টেজ পোর্শনের সাথেও ম্যাচ করতেছে। তো তুমি চাইলে ট্রান্সফরমার T1 বা T3 থেকেও ক্যালকুলেশন শুরু করতে পারো, অর্থাৎ এই লো ভোল্টেজ থেকে ক্যালকুলেশন করে এপাশে এবং এখান থেকে এপাশে, সিমিলারলি এখান থেকে এপাশে বা এখান থেকে এপাশে আসতে পারো। সো ভোল্টেজের বেসটা আমাদের পার ইউনিট ক্যালকুলেশন করার জন্য পাওয়ার সিস্টেমের যে ডিভাইসের সাথে ম্যাচ করবে সেখান থেকে আমরা ক্যালকুলেশন শুরু করব। তার কারণ হচ্ছে ট্রান্সমিশন লাইনের ভোল্টেজটা ট্রান্সফরমারের প্রাইমারি থেকে সেকেন্ডারিতে শিফট হওয়ার সময় অথবা সেকেন্ডারি থেকে প্রাইমারিতে শিফট হওয়ার সময় চেঞ্জ হয়ে যায় রিগার্ডিং দ্য ট্রান্সফরমার রেশিও। সো দ্যাটস ওয়াই ভোল্টেজটা ডিভাইসের যে ডিভাইসের সাথে ম্যাচ করে ক্যালকুলেশন সেখান থেকেই শুরু করতে হবে। তা নাহলে কিন্তু তোমরা ম্যাথে ঠিক মতো করতে পারবা না, আই মিন ম্যাথ হবে না অ্যাকচুয়ালি পার্টিকুলারলি। এবং আরেকটা বিষয় হচ্ছে পাওয়ারের বেসটা কি দেওয়া আছে এবং এই বেসটা কার সাথে ম্যাচ করতেছে এটা আমাদের হেডেক না, কারণ ট্রান্সমিশন লাইনে পাওয়ার চেঞ্জ হয় না। ট্রান্সফরমারের প্রাইমারি থেকে সেকেন্ডারিতে আসলেও পাওয়ার সেম থাকে, পাওয়ার আনচেঞ্জড অবস্থায় থাকে। সো পাওয়ারের নতুন বেসটা কার সাথে ম্যাচ করলো এটা ম্যাটার করে না, বাট ম্যাটার করে ভোল্টেজের বেসটা কার সাথে ম্যাচ করলো। সো যদি তোমাদের বলা থাকতো যে নতুন বেস ভোল্টেজটা 10.45 কেভি ধরে করো আর পাওয়ার 100 MVA, তাহলে তোমরা দেখতে পাচ্ছ 10.45 কেভি মোটরের সাথে ম্যাচ করে, তার মানে তোমার ক্যালকুলেশনটা মোটর থেকে শুরু করা লাগতো, এখান থেকে শুরু করে এই পুরো এই পর্যন্ত আসা লাগতো। সো বেস ভোল্টেজ কোন ডিভাইসের সাথে ম্যাচ করে ক্যালকুলেশন সেখান থেকে শুরু করতে হবে। আর যদি তোমার বেস ভোল্টেজ কোনো ডিভাইসের সাথে ম্যাচ না করে, যেমন বলা থাকলো এখানে যে তোমার বেস ভোল্টেজটা হচ্ছে 9 কেভি, সো 9 কিলো ভোল্ট কারোর সাথেই ম্যাচ করে না, সেই ক্ষেত্রে তোমার স্বাধীনতা, তুমি চাইলে জেনারেটরের এখান থেকেও শুরু করতে পারো, চাইলে মোটরের পাশ থেকেও শুরু করতে পারো, চাইলে ট্রান্সফরমার থেকেও শুরু করতে পারো, যদি বেস ভোল্টেজ কোনো ডিভাইসের সাথে ম্যাচ না করে। সো তোমার কোয়েশ্চেন পরীক্ষায় আইদার বেস ভোল্টেজ বলে দেওয়া থাকতে পারে, যেরকম এখানে বলে দেওয়া আছে, তাহলে যে ডিভাইসের সাথে ম্যাচ করে ক্যালকুলেশন সেখান থেকে শুরু করতে হবে, অথবা তোমার বেস ভোল্টেজ পরীক্ষায় বলে দেওয়া নাও থাকতে পারে, যে ডিভাইসের নাম বলে দেওয়া থাকতে পারে, যে পার্টিকুলার জেনারেটর অথবা ট্রান্সফরমার T1 এর রেটিংটাকে বেস ধরে করো। তো যদি বলে থাকে পার্টিকুলার ট্রান্সফরমারের T1 কে রেটিং ধরো, তার মানে তোমার বেস পাওয়ার 50 MVA কে রেটিং ধরতে হবে, বেস ভোল্টেজ কে 22 কেভি লো টেনশন সাইড অফ ট্রান্সফরমার, হাই টেনশন সাইডের জন্য 220 কেভি কে রেটিং ধরে তোমাকে ক্যালকুলেশন এখান থেকে শুরু করে ডান দিকে এবং বাম দিকে এগোতে হবে। অথবা যদি কোশ্চেনে বলে দেওয়া থাকে এমন কিছু যা কারোর সাথে ম্যাচ করে না, তখন তুমি যে কোনো এক পাশ থেকে ক্যালকুলেশন শুরু করতে পারবে। সো এটা হচ্ছে আমাদের কোশ্চেনে কিভাবে বলা থাকতে পারে এবং আমরা ক্যালকুলেশন অ্যাকচুয়ালি কিভাবে সলভ করব। সো পার ইউনিট ক্যালকুলেশন নিয়ে আমরা ইন ডিটেলসে ডিসকাস করব এবং খুবই আস্তে আস্তে আমরা আমাদের লেকচারটাকে সময় নিয়ে এগোচ্ছি, কারণ এটা খুবই ইম্পর্টেন্ট এবং তোমাদেরকে খুব ঠান্ডা মাথায় কাগজ কলম নিয়ে বসে নিজ হাতে ক্যালকুলেশন করে এই কনসেপশনটাকে গ্রো করাতে হবে। সো এতটুকু হচ্ছে ফার্স্ট পার্ট, যে ফার্স্ট পার্টে আমি আগের লেকচারগুলো একটু রিভিউ করলাম, ইম্পর্টেন্ট জিনিস পার ইউনিটের অ্যাডভান্টেজগুলো ডিসকাস করলাম, এবং এই পার্টিকুলার যে ম্যাথমেটিক্যাল প্রবলেমটা আমরা আজকের ক্লাসে সলভ করব, এই প্রবলেমটা কোশ্চেনটা নিয়ে ইন ডিটেলস ডিসকাস করলাম, যে কোশ্চেনে কি মিন করছে এবং আমাদের প্রবলেমটা কিভাবে সলভ করতে হবে এবং কি কি কন্ডিশনের জন্য কোন কোন ওয়েতে সলিউশনটা করতে হবে। সো নেক্সট পার্টে আমরা এবার এই ম্যাথমেটিক্যাল প্রবলেমটার সলিউশনটা দেখব।